Hello everybody. In this video, we're going to learn about matrix operations. In this part of the course, we want to solve systems of equations. And we've learned about different equivalent ways you can write a system of equations, either as separate equations in terms of the variables, or you could group these terms and write down a vector equation, which involves scalar multiplication and vector addition. Or you could gather the coefficients into a rectangular grid of numbers, which we call a matrix, a vector variables, and a vector with constants. And all these are equivalent expressions. Now we want to use the fact that these expressions all mean the same thing to define a new operation, something called the matrix vector product. And so over here, in these last two forms, in both cases, the left-hand sides are equal to the vector PQ. Well, if two sides are equal to the same thing, then those left-hand sides should be equal to each other. And we'll use that to define a new operation called a matrix vector product. So if you have a matrix of numbers times a vector, and in this video, we'll only be talking about 2x2 matrices and vectors with two elements in them. We'll define the matrix vector product to be this linear combination. Right? This involves some scalar multiplication. Right? So here, this first vector would be a times x and c times x. The second vector would be b times y and d times y. Then you use vector addition to add those up, and the result is a vector. Ax plus by is the first component, and cx plus dy is the second component. And that's how we'll define it. To make it more clear, here's a numeric example. Let's say we have the matrix 1, 2, 3, 4 times the vector 5, 6. When you multiply those together, the result's going to be another vector. You can think of it in terms of scalar multiplication and then vector addition. And so multiply these by 5, multiply these by 6, and then add across. You'll get 1 times 5 plus 2 times 6. That's 5 plus 12, which is 17. On the bottom, you'll have 3 times 5 plus 4 times 6. That's 15 plus 24, which is 39. So this matrix times this vector gives you this vector. Let's do another example. Let's say you have the matrix 7, 5, 5, negative 4, and you want to multiply that by the vector negative 3, 8. Once again, you can think of it as a linear combination here, right? The first column times negative 3 plus the second matrix column times 8. So across the top, we have 7 times negative 3 plus 5 times 8, which equals 19. And across the bottom, we'll have 5 times negative 3 plus negative 4 times 8. You add those up, you're going to get negative 47. So this matrix times this vector results in this vector, 19, negative 47. Now, because we like to identify patterns in mathematics, because they help us remember things and draw connections, this pattern up here, right, this is reminiscent of the dot product. Right? Remember the dot product of two vectors, say v and w, if v has entries v1, v2, and w has entries w1, w2, the dot product of those vectors is defined as v1 times w1 plus v2 times w2. So this calculation that we're doing, this matrix vector product, when you write it out, the top component is a times x plus b times y. If you have something times something plus something else times something else, you could also write that as a dot product. In this case, the first entry is the same thing as ab dot xy. The second part of the solution, this vector, cx plus dy, you could write as the vector cd dot with a vector xy. And so you could write this entire formula using dot products. A really useful way to think about this is imagine partitioning this matrix. Imagine drawing a dotted line that separates the rows. And then think of each row as a vector. Right? This first row, A, B, let's call that vector R1 for the first row vector. And then CD, let's think of that as vector R2, the second row vector. Also, let's take the vector of values here, x and y, let's call that vector v. Then here's a very shorthand notation you can use to think about or help you remember how to calculate a matrix vector product. It's the first entry is row 1 dot v, and the second entry is row 2 dot v. Right, so for example, the same example we did above, we could write it in this format. So 75 dot negative 38, calculate that out, you get 19. Then the second row, 5 negative 4 dot negative 38, that gives you negative 47. Right, it just helps you proceed more quickly to the answer, so you don't have to write this intermediate step of vector combinations. You can just proceed to calculating these dot product patterns. Now, another thing we can do is we can do repeated matrix vector products. Let's say we have an expression like this. Here we have a matrix times the quantity of a matrix times a vector. Now, algebraically, this makes sense, because we have to do what's inside the parentheses first, right? So we'd multiply this matrix times this vector. The result is a vector. And then, after that inner multiplication is done, we'll have a matrix times this vector, and the result will be another vector. So in this case, on the inside, we have the matrix 4, 1, 3, 6 times a vector 2, 5. Right, so to calculate that, I have 4 times 2 plus 1 times 5 on the top. On the bottom, we'll have 3 times 2 plus 6 times 5. And when you calculate those out, you'll get the vector 13, 36. And that vector still needs to be multiplied by this outside matrix, 2, 3, 5, 7. So once again, to multiply this, think about dot products. 2 times 13 plus 3 times 36. That equals 134. For the bottom entry, 5 times 13 plus 7 times 36. Calculate that out, you'll get 317. It's a pretty big vector. Now, mathematically, this leads us to an interesting question. We're very used to the associative property, kind of shifting around parentheses. Is it possible to combine the matrices first instead of doing the matrix vector product? In other words, is this possible? Could we shift the parentheses and make sense out of this? Right? What would it mean to multiply a matrix times a matrix? Right? In other words, if we want these two things to be equal, that will actually tell us how matrix multiplication must be defined. Right? The reason I'm showing you this is I want to make sure that these aren't just magical formulas which somebody invented. They're formulas that are determined or calculated to keep mathematics consistent. If these two sides of the equation were not equal, then that would be bad. So we figure out how we have to define this operation to force these sides to always be equal, no matter what the matrices and the vectors are. Now to do that, we just need to use some algebra. It's not too bad. In fact, we'll see dot products appearing once again. So we'll start off by just putting some variables in for each of the matrices and this vector. If you calculate this first inner matrix vector product, you get ax plus by and cx plus dy. And then calculating this matrix times this vector. It's long, but it's doable. We'll have P times the first part plus Q times the second part. It's the first entry. For the second entry, we'll have R times this first part plus S times the second part. It gives us the second entry. Now use a little bit of algebra, distribute these numbers through, and then regroup in terms of X and Y, and then you'll get this expression here. And the way you could calculate this expression as a matrix times a vector, right? The coefficient of X is right here. This coefficient of Y is right here. The second coefficient of X is down here. And this second coefficient of Y is down here. Right? So multiplying xy times this one matrix has the same effect as multiplying xy times this matrix and then times this matrix. Right? So matrix multiplication of these two matrices must, in order for mathematics to be consistent, matrix multiplication must be defined in this way. And once again, dot product patterns are showing up, right? Each one of these entries is a number times a number plus a number times a number. So that tells us that matrix multiplication can also be expressed with a dot product. So just copying that formula from the previous slide, this is how we must define matrix multiplication. In terms of dot products, the way we would think about this is the matrix on the left, we're going to partition or divide that into two rows. I like to draw this dotted line right here across. It's the same thing we did when we defined the matrix vector product. So draw this dashed line here. For the second matrix, the right-hand matrix, draw a dashed vertical line. So we divide the first matrix into row vectors and the second matrix into column vectors. And then each entry is going to be a row vector from the first matrix dot with a column vector from the second matrix. For example, this first value here, right, that'll be the vector PQ dot with a vector AC. P times A plus Q times C gives us that value there. Right, so in your mind, you might want to think of the formula like this. And this will help us calculate it. So let's go ahead and do some examples. Right, the more examples you do, the easier this will become. So if we want to multiply the matrix 2, 3, 4, 5 times the matrix 9, 8, 7, 6, go ahead and partition that first matrix into rows, that second matrix into columns, and then do your dot products. For the top left entry, we'll do the dot of the top row times the left column. 2 times 9 plus 3 times 7. That's 18 plus 21, which gives us 39. The top right entry is the top row vector, dot with a right column vector. 2 times 8 plus 3 times 6. That's 16 plus 18, which is 34. The bottom left entry is the bottom row, dot with the left column. 4 times 9 plus 5 times 7. That's 36 plus 35, which is 71. And finally, the bottom right entry is the bottom row, dot with the right column. 4 times 8 plus 5 times 6. That's 32 plus 30, which is 62. So the matrix product, or the matrix product of these two matrices, is the matrix 39, 34, 71, 62. Let's do one more example. The matrix 3, 1, 0, negative 2 times the matrix 4, 0, 1, 5. Right? Top left is top row, dot with left column. 3 times 4 plus 1 times 1. That's 13. Top right is top row vector, dot right column vector. 3 times 0 plus 1 times 5, that's 5. The bottom left value is the bottom row vector, dot the left column vector. 0 times 4 minus 2 times 1, that's negative 2. And finally, the bottom right vector, that's the bottom row vector, dot with a right column vector. 0 times 0 plus negative 2 times 5, that's negative 10. So the product of these two matrices is the matrix 13, 5, negative 2, and 10. And just a couple of notes on these calculations. In general, if you have two matrices, it's not commutative. Matrix M times matrix N is usually not N times M. In a few special cases it will be, but in general it's not commutative. So the order makes a difference. The second interesting matrix fact, this is a very useful matrix here. We'll call this matrix I. It's the matrix 1, 0, 0, 1. If you multiply the matrix I times any matrix M, right, using our same partitioning as before in calculating dot products, the result is just the matrix M again. And you can also check in the other direction. M times the matrix I is also equal to the matrix M. So multiplying any matrix times the matrix I times the matrix 1, 0, 0, 1 does not change the value. This special matrix I is called the identity matrix. And I to matrix multiplication is similar to the number 1 in normal or scalar multiplication. Just like multiplying a number times 1 does not change its value, multiplying a matrix times I does not change its value. And so that's useful to keep in your mind. Identity matrices will be useful. They'll come up a few times in what follows. So, since you learn math by doing math, you should try a matrix calculation. Go ahead and try to calculate the product of the matrices 1, 2, 3, 0 times the matrix 5, 1, 2, 4. So you might want to partition these matrices, the first into rows, the second into columns, and calculate your dot products and see what you get. All right, that's an introduction to matrix operations, specifically matrix vector product and matrix product. Two very useful things in what follows. Thanks for watching.